Welcome to today's course. In fact, today is a little bit special in that, where is it, lights, projection. In that it's some kind of mashup because last year this same course or this lecture was given by Jean-Pierre Hubot, who was presenting a bit privacy-preserving techniques from his lab, and he was talking a little bit about SMC, while we work mostly with FHE, and we'll talk a little bit about PIR and a fourth acronym that I forgot. So we took JP slides and kind of adapted them a bit and made it a bit more understandable. So I try to present these slides to you. So SMC is secure multi-party computation. Then we have the HE, the homomorphic encryption. The ZKP, I forgot, the zero knowledge proofs, and the private information retrieval. So all four things are in fact used to increase the privacy of the communication, the privacy of the data storage, and the privacy of this data retrieval. All four of them have advantages, disadvantages, and I will go through all four of them, and at the end make a very small comparison. You're not supposed to know all the details and all the gory mathematical foundations of these things, but still know a bit what goes where and how you can use them, what is the good points and what are the bad points of each one of these four. Okay, secure multi-party computation. The secure multi-party computation is something where you want to compute something together if you don't trust the other guy. So if you trust the other guy, it's very simple. You make a network connection and you just exchange the data and everybody calculates and everybody's happy. But sometimes you don't trust the other guy. You might not trust him for not giving you the correct data. You might not trust him for looking at your data. You might not trust him for selling your data somewhere else. For example, elections. You might have everybody votes yes or no on a given cause, and then you want to look what is the total number of yes, what is the total number of no. But you don't trust that the others will not say whether you voted yes or no, so you can use this with a secure multi-party computation. Same thing also for auctions. So if you have some, for example, the EU wants to buy, or Switzerland wants to buy new fighter planes and asks everybody to make a bid, and then the lowest bidder will get the plane. So you could also do this with a secure multi-party computation where every bidder will send encrypted his bid to Switzerland, and then Switzerland could compute and find the lowest bidder without knowing the higher bidder's value. So that would be the goal of the SMPC. More examples, distributed data mining. So if you have some kind of user data that you have because, for example, of user visits at your site and you want somebody else be able to make statistics on them, but you don't want to give the data, so you can also use secure multi-party computation. They can send you the query, you can work on the query and send back the query, and SMPC even lets you do it double secure in so that you don't know what the query that comes in is, and that the query does not know your data set but only knows the result. So that could be, for example, the query wants to know who went to this one web page, and then you do his query, but it's all encrypted, so you don't know he's interested in that web page, and you send the result back to him, so he does not know what the other hits are on your web page. Same thing with database privacy. Same thing with like with websites. So in cryptography, there is a saying that says every cryptographic problem can be solved with a trusted third party. So if you assume that there is a trusted third party that everybody trusts, you can solve all cryptographic problems, and you can forget about anything like homomorphic encryption and secure multi-party computation and all that, because you just go to this central place and you do exchange with that central place. The central place can give public keys of other people, can give encryption keys, can give whatever you want, and you solve the problem. Unfortunately, as cryptographers, we don't trust these central parties because these central parties then will know everything that you do. But we don't want to have somebody central knowing everything we do. But we can use this, trusted third party as a model of what would be possible. So in the following slides, we start with a trusted third party, where we suppose we have somebody we trust. We suppose we can exchange data with him in a secure manner, and that he never lies, he never cheats, he never eavesdrops, he never does anything bad. And then going on from there, we can look what things we want to do with secure multi-party computation, what attributes we need from the secure multi-party computation. Okay, let's see. How do we define security? Okay, must be mathematically rigorous, must capture all realistic attacks. And we want to define this security, but for the very general scenario, it's often hard. So we will compare this ideal, so with a trusted third party, against the real world approach where we don't have a trusted third party. Let's say we have different parties, so not just one, but different parties. That can be, for example, the voters or the bidders in the auction model. And they want to compute any function. Okay, so for the voting, it would be the total number of yes. For statistics, it would be how many people went to this website. And in the ideal world, so in the trusted third party, we just send everything to the trusted third party. He makes the computation and sends the results back to everybody, and everybody's happy. Now, in the real world, we don't have that, so we need to run some kind of protocol where we exchange messages and where we are always, or where we never trust the other parties, where we also always suppose that the other parties could be in fact cheating or snooping or changing messages or not going according to the protocol. We would like to have our real world protocol, so the secure multi-party computation, behave as if we have the ideal world, as if we have the trusted third party. Okay, here we have this judge who is in the middle, who is doing the right thing. And we say a protocol is secure if it emulates this ideal setting, where this ideal setting where we have this trusted third party, and we say the protocol is secure if all the attacks that can happen with the trusted third, if it is protecting against all the attacks that you could have with a trusted third party. So if, for example, I say, well, this protocol is not secure because somebody could get my data, well, it's the same thing here in the trusted third party model, so that's not a valid attack. So you need to have an attack that is in the trusted third party model, and then you can also attack it. Then it also counts as an attack on the real world scenario. We have these different possibilities of adversary models. So yeah, we might have or might not have corrupt participants, and corrupt participants might be corrupt in two ways. They might be semi-honest, or sometimes you say honest but curious. Honest but curious means they participate in the protocol as they should, but they will try to listen to the messages. They will try to read what is happening. They will try to snoop what you are trying to calculate. On the other hand, we can have malicious models, malicious participants that will not abide to the protocol. Malicious nodes that will do whatever they want. They may send wrong messages. They may stop corresponding with the other models, with the other nodes. And depending on the attack, you either have honest but curious or malicious. Usually what people say is that we have an honest but curious model. So the nodes, they abide to the protocol, but they might snoop. And the malicious nodes, usually you keep them down to some kind of threshold. So you say out of the 10 nodes, I only have 1/3 that are malicious. And as long as I only have 1/3 who are malicious, my protocol will finish. And then you say, furthermore, even if all are honest but curious, then they will not learn anything like that. So that's usually what you do then for the real world scenario. And that is the common adversary models that are used not only in SMPC but also, or not only in SMC but also in other settings. Okay, then we want the protocol to be correct also. So if we have these input values and the function, at the end, every node, every honest node should get the correct result. Of course, a malicious node will not get the correct result, but we don't care about the malicious nodes. So if the malicious nodes only get garbage, that's their problem, that's not our problem. We also want to have privacy, so that's the honest but curious protection. We also want to have privacy, so no node should learn anything about what we're doing. Okay, so for the simulation, that's in fact a real world view. So in the simulation, in the real world view, we want it to be indistinguishable from the trusted third party, so from the best case scenario. While working on these single, yes? Oh no. Yeah? No, this is with regard to the attacking model. So indistinguishable, so if you can attack the real, world view, then you can also attack the ideal world view and vice versa. So indistinguishable from that point of view. So from the attacking point of view. So there should not be an attack on the real world model if the same attack cannot also be done on the trusted third party model. So if your model is less strong than the trusted third party model, then you don't have a good model. So you want our simulation, you want our real world model to be as good as the trusted third party model. So from the attacking point of view. So from the attacking point of view, it should be indistinguishable. Yeah. Make sense? As I say, I'm retaking slides that have been written by another professor and translated by TAs. So I'm trying as best as I can to answer your questions. But yes? Okay.
So like these distributions are exactly the same, where are we saying that computationally you cannot
Aha, okay, so comparing simulation with the real world view. Yes, yeah, then there should be the same, yes. Yeah. Yeah. Okay. So while working on this secure multi-party computation, Kilian, they came up with this, what is called oblivious transfer. So oblivious means that you don't know what the other party is interested in. And in fact, this oblivious transfer block seems to be a very basic building block with which you can build up very complex systems. So you start just with this one block, and using this one block, you can then do all kinds of very complicated combinations. You can do later logical blocks like AND and XORs, and using these AND and XORs, you can implement any function that you want to apply on the data. Problem is that these blocks, they get multiplied by a lot. So even if you just have a very simple function where you want to compare two numbers, you need to have a lot of these AND and XOR gates, and so you will have a lot of these oblivious transfer blocks. So usually these secure multi-party protocols get quite big. Here in this, this oblivious transfer block has inputs and outputs. So the sender is the one who has the data, and the receiver here is the one who wants to have either one of the data. So let's say the sender has two values, one value for a database with just two entries, and the receiver wants to get either one of the entry. But the sender does not want to give both entries to the receiver, and the receiver does not want to tell the sender which entry he wants. Now the question is, how can the sender and the receiver proceed so that the sender sends the data to the receiver and the receiver will be able to get exactly one result, the result he's interested in, without the sender knowing what the receiver wants and without the receiver knowing the other data entry. So these are the two messages here that come in, and this is the message that the receiver wants. So this is very, very general. This is the protocol that they will do. In fact, here the raw that you have here is the data entry that the receiver wants. So raw is either 0 or 1. Okay, so the receiver wants either 0 or 1, and the sender will start by giving some kind of seed to the receiver. And then from this seed, the receiver will create a public key for raw, where he knows the private key, and he will create a public key for 1 minus raw, where he does not know the private key. So here comes now the honest but curious thing into play. We suppose that the receiver does not create two public keys where he knows both private keys. Now we suppose he's honest and he only has one private key. Either he has P0 or he has P1. Now he sends both of these keys to the sender. So the sender has two public keys. He does not know which of the public keys the receiver has the corresponding private key. He knows one of the public keys, he has the corresponding private key, but he knows not to the other, but he does not know which is which. So now the sender, he can encrypt the message M0 with P0 and the message M1 with P1. So it can be a simple gamma encryption here, and he sends that to the receiver. So the receiver gets two messages now, but only for one of the messages does he have the private key. And this one message he can now decrypt. So the receiver can get exactly the result he wants, and the sender does not know what the receiver wanted, and the receiver cannot decrypt the other result because he does not have the private key of the other public key. Now when this Kilian here made this oblivious transfer, he had some way of how the receiver needs to create this P0 and P1 in such a way that he only has one private key. But I will not go into the details here. So there is a way where you can make two public keys, but you only have the private key out of one. So this is now secure against the semi-honest adversary, because as I said, if the receiver cheats and has two private keys, then of course he can get both messages, but we don't want to do this here. And we can generalize this even to have some 1 out of k oblivious transfer. So saying we can, if there are k messages, we just send k public keys, and we only have a private key for one of these public keys, and then the sender will encrypt everything, send it to the receiver, and the receiver will only be able to decrypt one public key. Now, a big problem with this is, of course, that the messages are huge. I mean, you have to send public keys for all the entries that you want, and then the sender needs to encrypt everything to all these public keys and send all the encrypted messages back to the receiver, which is, of course, a lot of overhead. So if you want to do things like DNA matching or something like that, you get to enormous messages, like it can be multiple gigabytes just to look whether you have whether you find some SNP, some SNP, some DNA sequence in a database with a couple of thousand DNA samples only. So this is something very, very expensive, this secure multi-party computations for the moment. There are some, yeah. Just to say that there are quite a lot of optimizations now for special cases. If you want to do, as I said, this DNA sampling, if you want to look whether anybody, so if you have a database of DNA of people and you want to look whether anybody has this DNA sequence, there are a lot of optimizations how you can find whether anybody has this DNA sequence, and then if you know that somebody has this DNA sequence, you will be interested in that database or not. and then you can really request access. So there are a lot of optimizations in there, but it's always very special case optimizations, and it's very computing intensive, and it's also very network intensive. So secure multi-party computation for the moment is not done on a large scale. Yeah.
So you said that it's security listening and security.
Yeah.
Can you tell me exactly how it works with the malicious adversary? So it shouldn't be secure, right? But why? Like why?
For a malicious adversary?
Yeah.
Okay. So if I have a malicious receiver, what can he do? Okay, so the receiver here, he will send these two public keys to the sender, but we suppose he only has one private key. So what could a malicious receiver do? Have both private keys. And then what can he gain? Exactly, he gets both messages. Yeah. That's a malicious attack here. So you suppose that in a trusted third party, you only get the message you're interested in because you have this trusted judge. So you will not be able to get the other message. But now here with a malicious receiver, you might get the other message. So you're not as good as a trusted third party. So this is not the optimal protocol if you don't do it right.
It's kind of like it's kind of like we follow the protocol, but we can actually send all the messages just related to someone else, right?
Sorry, we can?
So we follow the protocol exactly.
Yes.
But we can send all the messages to like Eve, right? And you can try to extract some information.
Exactly. Well, you yourself are Eve, if you want to. Yes, yes, yes. Yeah, yeah. You can, for example, honest but curious could, for example, be a web server. He's honest. He's giving you all the web pages you ask him for. But you could say, oh, he's interested in debt handling, and so perhaps he has a debt, and perhaps I should send him ads for getting rid of his debt or something like that. So he could attack you like that and learn more from you than you really wanted to tell the web server. So this is the honest but curious. Or usually honest but curious is very bad in a medical setting. So if you have medical records, and then if you want to retrieve these medical records, and then if the server learns anything about your intentions, be it about your search requests, if you're a doctor and you make search requests on HIV, and you just have a patient at a given time, if you learn that the doctor had the patient at this given time and made requests for HIV, well, you can think that probably this patient has HIV. So that would be honest but curious. You're honest, you're replying to everything the doctor asks you, but you're curious, so you take all the messages and you make your conclusions. Okay? Yeah. Okay, yeah, some feasibility studies here for SMC. As I said, I'm not very, very fluent in secure multi-party computation, but so this T here, this is now the threshold of malicious nodes. If you have less than m divided by 3 nodes, you can make it for any function. Please don't ask me for the proof of it. If you have half of the nodes, and you have a broadcast channel, it seems you can still do any function. And if you have more than half of the nodes that are malicious, you cannot do all possible functions anymore. So all possible functions like search or compare or extract. Okay. And as I said, the challenge is the efficiency of the protocol on large data sets. So Jean-Pierre Hubault, he's in his lab, they are mostly working with medical data sets, either DNA or just generic sets from hospitals, where we have all the patients' data with why they came in, what illness they had, what treatment they received, how good it worked, and this is very sensitive data that I don't want to give out to anybody. So you want to you still want to be able to do research on this data, and for this they would like to do some secure multi-party computation, but the problem is the thing is so slow that so far there have been very, very few implementations. So there are some companies who do that, some data analysis, there are some secure key sharing companies, but it's really, the idea is very nice. The idea is you have this big black box with this very secure protocol, and you can send messages around, and everything is calculated completely anonymously. So you can make database retrievals, you can make computations, but the messages get so big, so fast, that usually you just don't use it. It's just too big of a hassle. But it's very nice, and for quite a couple of years they were hoping that in fact the computation, that there is some kind of breakthrough where all of a sudden it will be much faster. And in fact there has been a breakthrough, but not on the research part. There has been a breakthrough by Intel. You know what the breakthrough from Intel is that gave kind of the death mark to secure multi-party computation. Intel added something to their chips which kind of rang the death bell for this thing. No? One of the latest additions to Intel, where you can have some private computing inside of your processor. The SGX, exactly. So you have the SGX extension in Intel processors, where you are supposed to have some secure, completely blinded from the outside environment, where you can be sure that if there is a program running in there, it is exactly the program you want, nobody accesses it, except by cache miss and ghost and all these vulnerabilities that came out beginning of this year, of course. But besides that, nobody can enter it. And if you trust this Intel SGX thing, then you can do all the secure multi-party computation. You can do it very fast, very efficient, with very low overhead. And this is in fact what people are using. They're just saying, well, we have to trust Intel anyway. We're using their processors anyway, so why not also trust them for the computing on this data? So this is what most of the people use nowadays. They use SGX. And well, from a cryptographic point of view, SGX is really hell, because you have to trust Intel. You have to trust they don't have the private key. You have to trust that they don't hit any bug, either on purpose or not on purpose. So from cryptography, SGX is really the worst solution that you can have, but it works. So a lot of people use it. Okay. That was the secure multi-party computation part. A bit less secure, but still very secure and more interesting because it's much faster, is homomorphic encryption. So homomorphic encryption comes with the idea that it would be nice if you could have your data in the cloud encrypted, so medical data again, or your private photos or whatever, and you want to ask the cloud to search, sort, edit your data on your behalf without having to download all the stuff all the time, then edit it and uploading it again. So what you would like to do is you would like to have a query, like find all my photos from last July, send that to the cloud, and then get the cloud to process your query, and then return the encrypted answers to you. So the cloud does not know what you asked, neither what it needs to return. And then on your computer, you could easily decrypt it. Of course, same thing would be nice, for example, for sending a query to Google. So you send the query to Google, Google does not know, and then gives you the reply back. More general, you want to send any encrypted input E of X, so E here is the encryption part, and then the server executes the program P on this encryption and returns on the result. But as you see, you encrypt X, so X here is the query, your input, and well, here the program that you want to execute, and then the server returns the encryption of this execution on X. So that's the idea of homomorphic encryption. And the thing here is that for some encryption, it has been known for a long time that you can do some actions on the encrypted data, and then even if you decrypt it, it's still the same. So for example, some encryptions give you the possibility of having additive homomorphic properties. So if you encrypt two numbers into, if you, for example, take L-Gamal encryption using elliptic curves, you encrypt two numbers. If you add these two numbers and you decrypt it, you get the addition back, which is a very nice property with elliptic curves. With RSA, I think you have to multiply to get the addition, if I remember correctly, because you have it in the exponent, but better look that up. Okay, so I go a little bit into details, so just some notation we have here. So we say we have an encryption scheme with a key generation. So key generation, it's an asymmetric encryption scheme. We have a public and a private key. We have encryption function and a decryption function. The plain text space is 0, 1, but it can be a multiple, so 0, 1 to the n, so having a multiple bit string. And then we can generate a key pair. We get the PK is the public key, and SK is the secret key. Sorry, I always say public and private. So PK is the public key, and SK is the secret key. And then if I encrypt using the public key this bit here, I get the encrypted string. And if I decrypt using the secret key, this C here, I get back my original bit. Then, yes, we want to have what is called semantic security. So we don't want to have deterministic encryption. We want to have non-deterministic encryption. Else, if we encrypt a 0 and we always get the same, that's not nice. We need to have some way that every time we encrypt a 0, we get another ciphertext. So that's, for example, L-Gamal using elliptic curves. That's the case. Every time you encrypt a 0, you take a random number and you use this random number to encrypt a 0. So every time you encrypt a 0 using elliptic curves in L-Gamal, you get always a different ciphertext. So this would then be semantic security. Because else, of course, if you always get the same text when you encrypt a 0, it would not be secure anymore. Okay, so we say it's indistinguishable by efficient algorithms. Okay, yeah, that's a bit much, but what we want is we want to be able to evaluate this function f here on the ciphertext. So C is the ciphertext, C is the encrypted text. And we want to evaluate this function on the ciphertext, and we get C star. And then we want to have that if we decrypt now the C star, we want this to be f of x. That should be B here, huh? Yeah, on the other, here we had encryption of B as C, so this x here should be in fact B, sorry. Okay, so this should be encryption under public key of C, and then we evaluate this function on the encrypted part, and if we decrypt this whole thing, we get f of x. Now, we have somewhat homomorphic encryption, and we have fully homomorphic encryption. Somewhat homomorphic encryption, there are quite a lot of possibilities. Fully homomorphic encryption is in fact quite rare and also, again, difficult to achieve. Yes? Okay, so this first use of this privacy homomorphism has been used here also by Radler, Aldeman, and I don't remember the D anymore, in 78 already. And they wanted to search encrypted data. So they wanted to be able to say, okay, I have this data that is encrypted on the server, and I want to search it and know whether the search string matches any data or not. Yeah, so RSA and L-Gamal, we can have multiplicatively homomorphic. If you use the Paille encryption, we can have it additively homomorphic. Here are some examples with details how you can do this. But the big breakthrough came only in a couple of years back, where they had some fully homomorphic encryption using lattices. So lattice-based crypto is a whole new field of crypto that is very nice, but yet very new still. And they were able to do fully homomorphic encryption. They still had a small error because they could not do as many multiplications as you wanted to. Because the encrypted values, they kind of deteriorated over time. Because as I said before, in El-Gamal you always have a random value that is added to do the encryption. Now if you always add or multiply your encrypted text, these random parts get multiplied so they can grow over time. And so if you multiply too many times, then you might get wrong results. So they had some ways of fixing that. I don't remember what they called it. Yeah, bootstrapping. They had some kind of what they called bootstrapping. So they were able to remove these random additions again to kind of clean up the encrypted data. But it was it's still very slow. So they could say like, okay, if you want to have only 10 multiplications and 10 additions, then we know how much noise to add, and then everything will be happy. But if you do an 11th multiplication, then everything will fall apart. So you could give these things in the beginning, say I want to do this many additions, this many multiplications, and then the system calculated how much random noise you need, and everything was happy. But they are still quite brittle, these algorithms, but I think that's some very nice thing to do, and yeah, you can do a lot of this. So multi-key, fully homomorphic encryption. Yeah, I don't want to go into that. That's a bit similar to what you do with secure multi-party computation. An application for this. So now there is an application. So as I said, Jean-Pierre Hubault in their lab, they're mostly working with medical data. Here's an example of what they did with this homomorphic encryption. So suppose you have different hospitals here, where each hospital has their patients' database. They don't want to share their patients' database, okay? They want to keep it for themselves. But they want to allow other doctors to access their database to make research or to find out what treatment works well with this or that illness. So they would like any query to be done on their database, but they don't want to give up their database. They don't want to give it in clear, and the researcher, in fact, also is very paranoid, and the researcher also does not want to give up what her query is. So both parties would like to be secure. So theoretically, you could do that in a secure multi-party computation. So they started out doing that in JP's lab, and then they found out that, in fact, the SMC is way too big. So as soon as you have more than like 100 or 1,000 patients, with more than 10 or 20 attributes, the thing just falls apart. I mean, you have like calculation times of multiple weeks just to have one simple query like that, where you want to know how many patients are female, more than 50 years old, and carry specific BRCA mutation. So this BRCA1, if I remember correctly, is some kind of DNA default where you have a higher probability of having breast cancer, if I remember correctly. So this might be a usual query. So what they do now is they use homomorphic encryption, and they do it in a very interesting way. So if they have 3 hospitals, so here K1, K2, K3, they create an aggregate public key K, which is just the sum of K1 plus K2, K3. So for those who know, do you know a bit elliptic curves? No elliptic curves? You only know a little bit? You only know RSA? So in RSA, usually you multiply the numbers if you do things, or you put them in the exponent. And in elliptic curves, you add or multiply. So if you multiply in RSA, you add in elliptic curves, and if you do the exponent in RSA, you multiply in elliptic curves. But just very, very short. So this is additive notation. So in RSA, the K would be K1 times K2 times K3, modulo the modulo, but here it is just plus. Okay, so each hospital has its own key, and then it encrypts now its data under this aggregate public key, and then there is a lot of magic behind that makes so that we have this collective key, aggregate key, so we have some kind of trust splitting. Then, of course, everything is encrypted, so it's always encrypted. At no moment in time anybody sees the clear text. If somebody wants to influence the result, that is detected, because as we will see later, with zero knowledge proofs, you can prove that the calculation that you did is correct without showing the actual calculation that you did. And if somebody does something bad, you also see it. So you see who cheated, because the guy who cheated will not have a correct zero knowledge proof. We don't know where the data comes from. So in this example, if this lady here searches for how many people have this BRCA1 mutation, then because we do this shuffle here, so an encrypted shuffle, we do it in such a way that nobody will know what the order is that came in, but we can prove that we shuffled in such a way that all the inputs are still in the outputs. It's a very nifty trick, this NEF shuffle. And finally, yes, so all the data provider's data is never given to anybody else, and there's also, we talked about differential privacy, and they also put differential privacy, so they kind of put the whole thing into this unlinks, all these steps, and then in fact they found out that A, nobody wants all the steps, B, all the steps are way too expensive, so if you do a query on like 100,000 patients, it still takes a couple of hours, so that's too long. It should only take a couple of seconds. So they started to take it apart and kind of make models and say, well, if you want to have only the result alteration detected, then we only use the zero knowledge proof. If you don't want to say where the things come from, we add the NEF shuffle, and they kind of made nice models that you can add or remove. And then as time goes by, computers get get faster, and that we find better algorithms, they will be able to put more blocks in there. Okay, yeah, this is the gory details of the unlinks workflow. I will not go into there. Exactly. Okay, so that is for homomorphic encryption. Now, homomorphic encryption is faster than secure multi-party computation. You need to trust more the server, because now the server might know what you're looking for. So you need to make extra care. But it's feasible, and in fact this unlinks is now being deployed in CHUV, between CHUV and the Hôpital de Genève, and I think, is it Fribourg or Bern, who are also participating. And within 2 or 3 years, we would like to have it Swiss-wide, so 15 or 20 hospitals who are using this unlinks to allow research on patient data without revealing what the patient data is and without revealing what the research questions are. Okay. Questions before the pause? Yeah.
So you said something like, here we should trust the server, right?
Yeah.
But in the previous one, in this computation, the server needs to trust every client, right? That he actually doesn't have this private.
Oh, well, no, this was in the very simple example. This was in the very simple example that I gave.
Okay,
Yes,
so
yes.
Like,
They are much more elaborate. So this Adelman, these people, they have a way. So if you look into their paper, they say how they distribute the RSA keys in such a way that they are sure that you only have one private key. Yeah. So that's already done, but it was big, so we just made a simple example and said, okay, this is just the honest but curious version. But it's in the paper, and in fact, it's not that complicated. If you look at it for like 15 minutes, I did it this afternoon, I understood it, but I forgot again, so. You can look at it, it's understandable, really. Yeah, it's not that complicated. Yeah. And then usually it's just some very simple algebra. So, One thing I like about elliptic curves is you don't always have the exponents, you only have multiplication, then it gets more easier to follow the proofs. Yeah. Yeah. Exactly. Okay. Other questions? No? Okay. Then see you in 15 minutes.